Welcome to Spring Lib.
Um, Once again, welcome to a new problem. This time we're dealing with proofs. We have a surface, and this is under Bragg's law. We have reflecting planes. And these are horizontal. These are horizontal reflecting planes, as you can see. Multiple reflecting planes. It so happens that there's incident angle. Coming in. So this is light. This is a light wave like that. This is a light wave, and the angle is incident at theta and bounces off at another theta if this position is an A. The same thing happens on the lower side, and so we have light coming in and bouncing off reflection. The gap between these two, you can call it d over 2, and the entire gap going all the way down is d. This is C, and this is D, and this is B. This is just diagrams of reflection of light. And so the wavelength is lambda, and our goal in the problem is to see that we can't find a couple of things. We can't find the wavelength. So we want to prove it that we can't find the wavelength lambda of this radiation, and also so we can't find lambda, and we can't find not just lambda, but also the gaps between the planes. These are the planes that you're looking at. These are the specific planes you're looking at. So we can't find the gaps, and we also can't find the lambdas, the wavelengths, and the reason why we're saying we can't find it is that we can't find these two by using Bragg's law. So using theta for different m's. Remember, m is the order. So we want to prove that you can't really find the lambdas, and then you also can't really find the gaps between the planes. Okay, so we have different planes right there. So assume that lambda is the wavelength of the incident radiation, and d is the gap between the planes. It can be a crystal planes, but this is the reflecting planes. That's the gap. M is the order, and theta is what we call the Bragg's angle. Think about Fort Bragg's military installation. So this is the Bragg's angle. So based on the Bragg's X-ray diffraction, we get to see that 2D sine theta equals to m lambda. Remember, going back to the diagram, we see what d is. D is the gap between the two planes. Theta is the angle of reflection, and then Lambda obviously is the wavelength, and so that's what we're using in this particular problem. D sine theta is m lambda. If we know m and theta, there's no way, if you know m and theta, you can see that in this equation, we still have two unknowns. We still have two unknowns. To solve an equation, you need only a single unknown. So if we had 2D sine theta and we wanted to solve for d, we would have to divide both sides by 2 sine theta on both sides, and so our d would become m lambda 2 sine theta. But you can see that in this particular problem, we still have if we know theta and we know m, but we don't know what lambda is, then we have a problem. And also you can see that if we had 2d sine theta equals to m lambda and we wanted to solve for lambda, we'd have to divide both sides by m, and so we end up having lambda equals to 2d sine theta all over m. And now in the problem, we do have m, we do have theta, but we don't have d. So then we're stuck. So you can see that even by knowing m and theta, knowing m and theta, we still have two unknowns. And those two unknowns happen to be lambda and d, so we can't solve for these two values. We can't solve for these two values. So that's kind of our conclusion in this particular proof. If you go back, you see initially we had to use Bragg's angles. We are given theta. We want to find lambda and d, and we assume that we're also going to have m. We have two planes, or multiple planes if you want to call them. These are reflecting planes. Our purpose and goal in this particular problem is to see that is it possible to find lambda and d given that you have m and theta. And you can see by using the Bragg's diffraction equation, we still end up having two unknowns, that's theta and m. And because we have two unknowns, even if we have two knowns, theta and m, we still have two unknowns. And so we can't really solve the problem. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.